Okay, let's talk about momentum. So momentum in physics quantifies how hard it is to stop a moving object. So objects with a large mass traveling at high speed have a large momentum, whereas objects that have a very low mass, low speed have low momentum. Another thing that's really important to remember is that momentum is a vector quantity. It's a vector quantity, so we care about its direction. So to calculate momentum, we do mass times velocity, and you'll notice that I've got two examples here. The only difference between them is that the velocity is to the right in the first one and to the left in the second. And notice that I've flipped the sign of the velocity. So plus 20 when it's going to the right, minus 20 when it's going to the left. You don't have to have that convention of right is positive, left is negative, but you do have to make a choice and stick with it. Now, you should be able to just do a quick run through of these and write down the momentum of each, or the velocity or mass of each of these, whichever one's missing, just using that equation P equals mv. Now, momentum is an interesting concept and a particularly valuable one to physicists because it's a conserved quantity. So imagine on all these particles I have on the screen here, those red arrows are supposed to represent the momentum vector for each particle. And the interesting thing is that if we add them together, so we arrange them nose to tail, you end up with this light red arrow on the left-hand side. That is the vector sum of the momentum. Remember that when you're adding vectors, it's equivalent to putting them end to end. And the interesting thing is that if you have those particles bouncing around and colliding with each other, but there are no external forces acting on them, so the wind isn't blowing them in one direction, or there's no magnetic field acting on them, the length of this red line and the direction of this pale red line never changes, because there are only internal forces acting on them. So in words, the principle of conservation of momentum says that assuming no external force acts, the vector sum of the momentum in a system never changes. Now we can use this principle of conservation of momentum to analyze collisions. So here I have two objects, a 2 kilogram mass and 5 kilogram mass, traveling towards each other. And we can calculate their momentum just by multiplying those together. We get 4 and minus 15. And so the net momentum is 4 plus minus 15. And so we know that the momentum to begin with is minus 11 kilogram meters per second, which means that when these objects collide, I'm going to assume that they stick together. Now, they don't have to, but I'm going to assume that they do. And if they do, we can use this information to figure out the speed that they move with after the collision, because we know that the momentum after the collision must also be minus 11 kilogram meters per second, and we also know that the mass is 2 plus 5 because they've joined together. So rearranging the equation, we can find that the velocity is minus 1.6 meters per second, so we know it's also traveling to the left, which makes sense, by the way, because look at, to begin with, we had more momentum. Our momentum was to the left anyway, and so if they're joined into one solid object, then it must be moving to the left in order for the momentum to be to the left. Now I want to apply the same principle, but this time starting with a stationary object that explodes, and now each one of those particles has its own momentum. When it was stationary, its momentum had to be 0, because its velocity was 0. But that means after the explosion, its momentum must also be 0. So if you add those vectors together, you can see that they just come back around, so showing that the momentum was indeed 0. Now, what if the object, usually someone asks me, well, what if the object was moving to begin with? Well, let's imagine it had a momentum to the right, and this time it explodes. And let's imagine that the particles have momentums that look like this. If we carefully add those together, we would find that they still add up to that original momentum of 12 to the right. Now, the next concept I want to look at is the change in momentum, which goes by the name of impulse, and it's really relevant to a lot of stuff in rocket science, actually. So here's an example of a rocket. We switch the rockets on at time t equals 0, and away it goes. Its momentum gets bigger and bigger as it speeds up. And what I want to do is take a close look at the change in momentum that has taken place. Newton's second law is what we want to make use of in this study. So remember that Newton's second law says that force is equal to mass times acceleration, and very quickly acceleration is just delta v over delta t, change in velocity over change in time. And so by substituting that in and multiplying both sides by delta t, we can see that force times delta t is equal to m delta v. M delta v is just the change in momentum, delta p. And so we have this useful equation, force times time, change in time, equals the change in momentum. So you can see that the rocket had its engines on for 12 seconds and exerted a force of 1,000,000 newtons. So the impulse there is just 1,000,000 times 12. So the change in momentum should be 12 million kilogram meters per second. And just to finish, some handy equations that we've looked at.